Welcome to the first plenary session, the awards talks. And this is going to be the only 30-minute talk of the event. The best award talk by Johannes Harling, joint work with Vedat Hadzic and Roderick Brown. And so I understand that some people have trouble with visas, but so Johannes will distribute this to his co-authors, and we proceed to the talk. So this is
So congratulations again for the Best Paper Award. And we are ready to start this special session. So plenary session. Please go ahead, Johannes.
Yeah, so thank you everyone for coming here. I'm going to present our collaborative paper, Closing the Gap, Leakage Contract for Processors with Transitions and Glitches. To give you a broad idea of what I'm going to be talking about, let's quickly recap what a side channel attack is. As you all know, a processor, cryptographic processor gets plain text as an input and outputs encrypted messages and signatures. However, that's not everything that's going on in the hardware world. A processor emits side channel information in the form of voltage differences, the magnetic field, the temperature, and timing of a certain operation. And this is obviously bad. This is something we want to avoid. And today I'm going to talk about power contracts, which target 3 of those kinds of side channel attacks. Now, as you know, an attacker might perform power analysis attacks on a cryptographic piece of hardware. A processor needs power to perform its computations. It needs it to maintain the values in its registers. And whenever a change in the value of a wire happens, then it draws power. And the main reason for that is the way CMOS gates work. They draw power whenever there is a state change within the circuit. And this can be exploited by an attacker by measuring the power consumption of some piece of hardware, performing a lot of different measurements, and then correlating the data to the power consumed, and thereby recover keys, which is something which is very bad. To avoid this, we employ masking. For instance, if we have order T masking, we split every one of our secrets into D random shares. And we do this in a way that when we XOR all of the shares together again, we get the original secret. Also, then our subsequent calculations are only performed on these shares. And an attacker which is able to observe up to T of these values during calculation is not able to recover the original secret because you would need D different shares for that. And if we perform this correctly and all of the shares are kept secret or handled in a way that the attacker is not able to get all of the shares, then the system is actually secure against power side channel attacks. However, the hard part is to actually get this correct. Now, we obviously need to verify that we got it correct. So how do we verify this? One way is to use physical evaluation strategies such as TVLA, which unfortunately require actual hardware. We need to make actual measurements. And in the worst case, we have only proven that this one piece of hardware is not attackable. and it might not even be applicable to other pieces of hardware with the same design. So we don't have any formal guarantees. So we employ formal methods. We use formal models to obtain strong guarantees about the security of our system, which allows us to rule out entire classes of attacks within that given model, of course. Now, in order to actually work with this in a formal way, we need to we need a model which is more practical than statistical correlations. So the T-probing model was introduced to do exactly that. In the T-probing model, an attacker is allowed to place up to T probes on any wire at one point in time and learns all the secrets, all the information that flows through them. So as you can see, as an example, in free probing, an attacker is allowed to place 3 probes, for instance, 1 at the first cycle of execution and 2 at the second cycle at a different location. And to verify that system is secure against such a T-probing attack, we need to ensure that any set of up to T observations are statistically independent of any of the secrets. Now, to give you an example of how this might look like if we employ software level masking. For instance, in this example, we have X1 is holding share 1 and X2 holding share 2 in our masking scheme. And then we execute 2 RISC-V assembly instructions which end things together. Now, as you can see, X1 and X3 do not interact in this code snippet, so there's no way these shares can be combined, and the system should be secure. No, that's actually wrong. The problem here is that under the hood, a processor does things which actually lead to combined leakage of X1 and X3. And the reason for that, in this case, is the way the CPU register file works. At the output of the CPU register file, an attacker that places a probe there is actually able to obtain X1 and X3 with just 1 probe, because there is a transition between the 2 values. Now, what we want to achieve is to have an end-to-end verification of an entire system. So we start with software, which might have vulnerabilities or compiler optimizations, which mess up our masking implementation. And we want to execute it on actual hardware, which might also introduce some problems like parallel processing or physical defaults like glitches. And as I said, our goal is to have an end-to-end verifiable system where there's no manual, no way of having a manual problem here. The way we achieve this in our approach is by introducing a power contract, which is composed of 2 parts. It first of all specifies the instruction set architecture on a functional level, and it arguments this with the leakage information that is added. And this allows us to have a separation of concerns between what the software and the hardware actually have to oblige by to make a system which is secure. We can, with this power contract, we are able to apply verification separately on the software and the hardware. And this gives us some benefits. First of all, for software verification, we verify that the software is compliant to the contract by verifying the some probing model, in our case, the T-probing model, against it. This is very nice because we do not need the actual hardware implementation for that. The foundry might not, the hardware developer might not be able to give us that. We are not able to obtain it, but we don't need it to verify the security of our system. And once the software is verified, it is compliant it is secure on any compliant hardware. On the other hand, we verify the hardware by verifying that all the leaks in hardware are actually contained in the contract. And this allows us to have, of course, a processor which can securely execute any software which is compliant to the contract, leaving us with very little re-verification to do compared to if we just directly compare the software to the hardware. So how do these power contracts actually work? They formally describe the processor in two ways. The first one is a functional specification, or the instruction set architecture, which includes architectural registers like the program counter, X1 and X2, also the register file, and a formal specification of what these instructions actually compute. And this instruction set architecture description is augmented with a leakage specification, which allows us to add certain details of the implementation, like micro-architectural elements of the register file. And we need to specify leaks which are possible within the contract. Each of those leak statements is one possible way of an attacker to place a probe. And in this case, if we specify that X1 and X2 are being leaked together, we mean that any possible combination of the two of the arguments are being leaked. So for instance, A and B or A XOR B. So how does a power contract actually look like? We chose C++ as the base language for our contracts because it's very approachable and most people know how to use it. And you can see here, this is a very, very simple implementation of an AND instruction in RISC-V. We just read the two source registers and AND them together and write it back into the register file to the destination register. Someone writing a contract will then have to add leak statements to specify what a processor is allowed to leak. In our case, for transition leakage, we have 4 different leak statements, and we need to add some variables which are used to track the microarchitectural state. To give you a quick note here, this is the leak statement which covers the leak that we saw earlier, which is the leakage between the current output of the register file and the previous output of the register file. And for that to simulate properly, we need to store the old value, the current value of the register file to a global variable, and then you reuse that in the next instruction. Now, the title of our paper is Closing the Gap. So obviously, we refer to the state of the art, which was there was a hardware and software verifier which could do these things. However, there needed to be a manual translation step, which is obviously very error prone and can introduce bugs which is very undesirable. And we added the capability of verifying glitches on the gate level, which was previously not implemented. In our contract, we have a unified toolchain which does not require any manual steps between verifying from the gate level to the software level. And we have glitch support, which is very important. I will talk about it in a minute. As you can see here, this is an AND gate with A and B as input and the output O. And what we want to model here is what an attacker can gain from placing a probe at the output O. The first leakage model that was introduced was called value leakage, and it just specifies the leakage of a gate by giving the value of the gate at the end of the cycle, which in this case is 0. The value state change diagram you can see here is basically an exaggregation of how a timing difference in the input A and B might have an impact on what is being received at the output O. So in this case, A starts with the value 0 and B starts with the value 1. And during the cycle, both of them change their value. So the result of the AND operation is still 0. However, due to an in this case, exaggerated timing difference, A changes its value before B, and therefore an attacker placing a probe at the output might actually be able to obtain some information about A and B, because when the power consumption of the entire cycle is being shown, then you can see the spike at the output O. As you can see, value leakage does not cover that, because the value leakage in this case would only cover the 0 and not the glitch which happens within the cycle. The same thing goes for transition leakage, which covers the value of the at the end of the cycle and then the beginning of the cycle. In this case, those are still 0 and 0, so the glitch is still not covered. A naive way of implementing glitch leakage and having a model that covers it would be to just combine all of the values of the inputs A and B at the beginning and the end of the cycle. As you can see here, this would cover 0 and 1. So this actually is a valid model for glitches. However, this covers a lot more than we want to. In a different example here, if A would have stayed 0 and did not transition during the cycle, we would still leak 1 and 0 because our model is just that over-exaggregating the actual leakage. The problem with that is, if we apply this, for instance, to the output of a register file, we are able to obtain all of the values of all of the registers within the register file. So a combination of x1, x2, x3, and so on would have to be leaked in this case. The problem here is an attacker with such high capabilities is kind of annoying, and we cannot really write a contract that is useful to us, because an attacker can basically read all of the values in the register file at the same time. However, in reality, this is not always the case. As you can see here in our refined glitch leakage model, we conditionally forward the leakage of the inputs depending on whether one of the inputs is stable at 0 or not. And this works in the case where both of them transition, because the leakage is still the same as in the naive glitch model. However, if A is stable at 0, we do not forward the leakage of B. And in this case, leaking 0 is okay, because the output 0 is also stable and stays at 0. So we have a much tighter bound on the actual leakage. And this allows us to write better leakage contracts, because as you can see here, in this example, the same assembly code as before is shown, and switching from x1 to x3 causes only the bit 1 of the register source 1 to change, and register source 1 bit 0 is actually stable at 1. And in this case, because you can see that here that the signal is fed into an OR gate, which just happens to behave exactly the same as an AND gate, but reversed, the leakage propagation is actually stopped at the one-hot decoding stage. And therefore, in this, when executing this code, x0 and x2 are not glitched at the end of the output, which allows us to use those registers securely during computation. A different example would be to switch from X2 to X3, which causes the bit 1 to be stable and the bit 0 to change. And as you can see, a different set of registers is actually being leaked. Unfortunately, as soon as one of the bits of the select signal changes, half of the register file is being leaked and half of it is still secure. But we can use this to actually write a contract that allows us to write secure cryptographic code. Now, for hardware verification, we formalize glitch propagation for all of the gates. So for AND and OR gates and all of everything else that's necessary. We then efficiently encode the circuit for glitch verification. And the actual verification procedure works by transforming the contract and the netlist into an SMT representation, recursively applying the glitch propagation rules to the netlist, and then verifying simulatability for each gate in each cycle, which is hard, but as I said before, we only have to do it once for the hardware, and after that, we perform software verification, which is a lot faster. For software verification, we use the power contract and the assembly program, feed it into a simulator, which gives us a leakage trace, which is basically just a symbolic representation of all the leakage that's happening. And we then feed that to a solver, which tells us whether there will be a problem with a given leakage model or not. Either it says this software is secure given this contract, or it tells us that it is insecure, and it even can tell us which secret is being leaked and in which line of the assembly code. So this is very handy for debugging your cryptographic implementation. And to implement such a leakage detection, any of the leakage methods can be used, like Coco, Mask-Reef, Silver, or Reef MSI. In terms of verification time, we implemented a contract for the IBEX processor and performed hardware and software verification, verifying the hardware against the contract compared to the previous iteration of power contracts, which took 35.5 hours. Ours just took 12.1 hours, even though our model includes glitches and transitions. For verifying the construct against software, we performed verification on a bunch of different gadgets and S-Box implementations. And for instance, when verifying the AES S-Box with DOM DEP gadgets, the Coco would take 4.1 hours, and our approach only takes 15.1 minutes. Now, to give you an idea of how to build upon this work, our glitch array contracts are end-to-end verified from the gate level to the machine code executing on RISC-V. However, we can go beyond that. One way of doing so would be to have a contract be aware of context switches which happen inside of the operating system. And a good approach of doing that would be to have a separate contract for the operating system at the application binary interface level. Another way of building upon this work would be to build contract-aware compilers, which are actually able to compile code which abides by the rules specified in this contract. Obviously, that's going to be hard, but we can try. And a third way of going beyond what we already have is to include another type of physical defaults called couplings, which are currently not supported by our system because couplings only happen depending on where wires are physically linked together. and we verify only the netlist of processor design, which does not include this information. So to recap, our work contains our work introduces leakage contracts for power side channel, which include glitches and transitions. We verify end-to-end security with two verifiers. One verifies the software against the contract, and we then verify that the software does not leak anything given the leakage model, and verifying the hardware against the contract by making sure that the contract captures all the hardware leakage. And we present a case study with the RISC-V IBEX processor. We have published a contract, and we performed experiments with hardware and software verification, showing that the system is actually working and can prove end-to-end security with glitches and transitions. Thank you everyone for your attention. I'll be now taking questions.
Thank you for the nice presentation. We have time for questions, please.
Hey, thank you for your presentation. That was very good. I have one question, point that I'm not very clear with. So it seems that you're, well, we know that leakages, they depend on the microarchitecture details of that CPU. So I'm unclear if your method is able to extract leakage model that maybe are not modeled in your contract, or if you have to model everything in the contract. For example, you model transitions, but what if the microarchitecture detail has a max that return to zero the data, so the model is actually more a Hamming weight model instead of a Hamming distance model. So could you provide more detail? Thank you.
Yeah, so in our case, the developer of this contract is actually able to make a call on how detailed this leakage is going to be, because you could write a contract which actually very closely resembles what the hardware leaks itself, or you could write a contract which just leaks the entire register file. It's up to the developer of the contract to find a good middle ground for writing a good contract that's actually useful and can facilitate good software, and on the other hand, not being too restrictive. And as you said, the leakage of the hardware itself is according to the T-probing model. So we refer to that when it comes to concerning between the Hamming weight or the Hamming distance. Does this answer your question?
Anyone else wants to come up to the microphone?
So in the same spirit, I have the similar question. How sensible to temperature changes is your contract, if it's resistant to model accurately in spite of changes like this?
So as I said, the verification of actual hardware would be referred to the T-probing model, and whether the T-probing model is actually a good representation of physical hardware. And this would have to be established at that point. I do not have any concrete information about how the temperature affects this.
Thank you.
So I have a different kind of question. Like, you seem to be using SMT solvers at some stage, and since I know a little about SMT solvers, sometimes the answer is not an unset. It's not a counter example. It's sometimes it just keeps running and running and never terminates. How often does this happen in your verification efforts? Does it ever happen?
No, this is obviously a problem with SAT solvers that they might take forever to verify a problem. However, in my experiments, this has never happened. The verification time is actually very consistent and is much below what you would expect because of the way this problem works. A SAT solver is actually very effective in solving it.
Okay, we have time for one more question if you have. Yes.
Can you hear me? Great. Thanks for your talk. Can you go back to slide, I think 45? Okay, sorry for that. Then it was, I'm not sure if it was earlier, there one where you showed the signal transition diagrams. Yeah, this one. Just a short question. When you model the glitches, what happens when you have a glitch on A or B? So when your input is already glitchy.
In the case that it is glitchy, so our actual model looks like this. If A or B are glitchy, then we will either forward or not forward the glitchy signal as an output of the AND gate. However, if only one of them is glitchy and the other one is stable at 0, then the glitch will terminate and not continue throughout to propagate throughout the rest of the circuit.
Okay, thank you.
Any more questions? And if not, let's take the rest offline and let's thank the speaker again. Remember these guys. So for the second talk of the session, we have fast and clean auditable high performance assembly via constraint solving. This is by Amin Abdul Rahman, Hanno Becker, Matthias Kanwischer, and Fabian Klein. And this is actually received wide support among those PC members who had an opinion, and also this has found actual practical use. And so let's welcome Matthias, who is giving the talk.
Thanks. I'm very happy to talk about our tool slot here today, and I would like to thank the PC for naming this the runner-up to the best paper. This means a lot to us because, I mean, for me, this was the by far the most painful paper to publish in my career so far. So thank you very much. I should also mention this short talk should be given by Hanno Becker, but he can't be here today, so I'm going to give the talk. So let me start with some motivation. I hope we can all agree that good cryptographic engineering is hard, and you often have to balance multiple different things. For example, you would like your code to be simple. So you might start with some C implementation. It's easy to read, easy to write, and there are some problems with this. For example, there is sometimes compilers introducing vulnerabilities into our code. So if you've saw the Clanger work or also Kyber/, sometimes compilers introduce timing side channels in our code, and we kind of want to avoid that. So we either have to use other tricks to stop the compiler from doing that, or we may just give up and just say we write everything in assembly. And for performance, we actually often do want to write it in assembly anyway. Then we can have control over what instructions are going to be used. So for performance, we often pick assembly anyway. And then we may even want to do more performance optimizations and optimize for a specific microarchitecture and take into account all the features of that and come up with code that works well on that microarchitecture. And some of my co-authors and also me, we have spent a lot of time optimizing for microarchitectures. And you can spend really months on if your microarchitecture is complicated enough, you can spend a lot of time on this. And if you then decide you want to optimize the same code for a different microarchitecture, you can still spend significant amount of time. Of course, not the same amount of time because you already know all the tricks, but you can still spend quite a lot of time to optimize for different microarchitectures. So, and yeah, some of us work for companies, and then when you write this sort of code, we get told, well, this might be fast and all very nice now, but no one else will be able to understand this or maintain this. So then you have need to do more things to be able to get this into production. And this is kind of annoying. So we try to find a better way to do things. And that's how we came up with this tool. So our goal was we want to write microarchitectural independent code and then leave this microarchitectural specific things up to a tool. And this tool is named Slothy. So where you feed in assembly, so you still have full control over what instructions are being used, but you ignore all microarchitectural things, so like latencies and how your pipeline works. You ignore that and leave that to a tool. And the tool then gets an architectural model. So this will be describing how your instructions look like. But since the tool is not going to change any instructions, we don't need to model the semantics of instructions. So you only model, okay, this is the instruction. It has these sorts of inputs, these are outputs, and these registers are inputs and outputs. And you may have to model some restrictions on what registers can be used for certain instructions. Then what you also feed into the tool is a microarchitectural model. So this will model latencies of instructions, throughputs of instructions, and any sort of other details of your microarchitecture. Our tool then translates this into constraints and feeds these constraints into a generic constraint solver that will find a instruction scheduling and register renaming that is optimal for this sort of models that we feed in. Let me give you one example here. So we looked at multiple different crypto systems. One of the things we looked at is the Kyber entity. And we had a paper at CHES 2 years ago where we had some handwritten assembly. And now we looked at this again and wrote this again in a cleaner way. So ignoring all the microarchitectural aspects. And you can see if you look at these instructions, you have like consecutive instructions that depend on the previous. So this will be very bad if this is an in-order CPU, and this will perform very poorly. And that's actually also what we see. So this code then gets slower than what we had before. And then we feed it into Slothy, and the results we get is actually very fast code again. In this case, it's actually faster than what we had 2 years ago. Don't get me wrong here. I'm not saying that you can't do this by manual effort. In fact, we know that you can do the same thing by manually doing all this optimization. So Vincent Wang, one of our co-authors in the previous paper, now has a handwritten entity that is essentially the same speed. So it's possible, but we think with this tool, it's a little bit easier, and you can do it for multiple different microarchitectures with relatively little effort. So let me tell you a little bit more about our contributions. So Slothy is an approach to do register allocation, instruction scheduling, and software pipelining. And we model this as a constraint satisfaction problem. We implemented this then with a generic constraint solver. In this case, we use CPSAT from Google. So our tools, but you could also use a different solver. we have looked at a bunch of different architectures. So we looked at both M-profile, the M-profile vector extension, and the A-profile neon instructions, and multiple different microarchitectures, so the M55 and the M85 implementing these MVE instructions, and the A55 and the A72 implementing the neon instructions. By now, we also added some more. So we have ARM Neoverse N1 and Apple M1 models modeling the, also implementing neon. And then we applied this to a bunch of different schemes. So we looked at post-quantum crypto entities for Kyber and the lithium, but we also looked at some FFTs that are relevant for signal processing, and we also looked at X2519 scalar multiplication. And for all of those, we either get performance that's as good as the handwritten assembly or even better. So what are the advantages of using this tool? We think we do get similar or better results. We can support multiple microarchitectures. We can write one clean implementation, then multiple optimize for multiple microarchitectures. We do think it takes less time, so development gets less time intensive this way. Some algorithm level experiments become easier. And actually the input to Slothy is executable. It's just assembly. So this makes testing a little bit easier. And also you don't have to learn an extra language. You can just write assembly as usual. And we can use software pipelining that I'll talk about later. We also think it eases maintenance and audit and formal verification. I'll talk more about that a little bit later. We comment on one thing that we often get asked. So for in-order cores, it's very obvious that this is very important to have good scheduling. And if you want high performance code, then you will need to look into scheduling. But we actually found that even for some out-of-order cores, the scheduling is very important for performance. So we get good results also on, for example, the A72. Okay. We give some more details on how we do this. So this is a very simple example, just 3 instructions. Just so you know how this roughly works. So we parse this assembly into a computational flow graph. This will be modeling all the dependencies between our instructions. And then we come up with constraints, modeling how we can change this program, maintaining its semantics. The way we do this is, let me start with the correctness. We introduce integer variables that will be modeling the output position of each instruction. So in the output code, each of the instruction will have one position, and then we model this as an integer variable. And we can place some constraints on this. The obvious one is that all of these positions need to be different. And for the correctness, we will need to model that all consumers of a certain value are after the producer. This means that for each edge in this CFG, we add a constraint that the output position of the consumer is after the producer. This is all that's needed for correctness. But it quickly turns out that this is not very useful. So if we just do this, we can't get any performance improvement. We need to actually do register renaming. We can also do this using constraints. So we need to, we introduce variables that model if a certain register is the output of an instruction. So for each instruction, we have these Boolean variables for each of the registers that could possibly be used as the output. So for the first instruction and the second instruction, we have these. For the third, we don't, because it was a multiply subtract instruction. So the inputs are, outputs are also the inputs at the same time. So we can't really pick what the outputs are. And then we place constraints on this. So the obvious thing is that for each of the instructions, only one register is going to be the output. And the other thing we need to model is that there's one value is like there's no overlap between different values. So the way we model this is we model the interval between between the producer and the last consumer, and then we place constraints that for each register these intervals of consumer and producer, they can't overlap. In this way, we can do register allocation. How much time do you have left?
like 10 minutes.
Okay, thanks. So now we can start with the interesting stuff. That is adding the microarchitectural constraints. So, and for some of the, or many of the ARM cores, you actually have nice manuals that describe you how the microarchitecture looks like. You can see for these instructions that we had in this examples, we have a latency of 4 cycles and a throughput of 2. So we can put this into our model and add constraints, meaning that here the consumer needs to be three cycles after the producer. And here you immediately see that this is not possible. So you can't, if you just have these 3 instructions, you can't find any scheduling where this is the case. So, but if you have a larger example and you have enough parallel computation, you will find solutions. But this is just to illustrate how the constraints work. I left out a lot of details here. So for the full picture, please have a look at the paper or the code. So some of the things I left out, so of course, you cannot always find the stall-free scheduling. So you need to somehow allow gaps in your scheduling. And then you minimize this number of stalls. We need to model multi-issue CPUs. So for example, the A55 is a dual issue CPU. So you need to model this kind of dual issuing capabilities. And sometimes you also have instructions that have issue constraints. So this can also be modeled. You need to model the different execution units in your CPU and the instruction throughputs. And this is very important for some of the cores we looked at. We do have forwarding paths sometimes that we need to model to get the best performance. And we actually also do have support to model dependencies through memory. So if you have stack spills, we can also model that. And one last thing that I want to talk about here is software pipelining, which is also sometimes called periodic loop interleaving. I'm not sure how familiar you are with this, but the idea is generally, if you have a loop, it sometimes makes sense to pull certain instructions into previous iterations or push them into next iterations to hide some latencies. And in general, you could do this over many iterations. For this tool, we restrict it to just 3 iterations. So you can have late instructions from the previous iteration or early instructions from the next iteration. And then you, of course, if you do this, you have to pull out the first iteration and the last iteration, so this is still correct. And we can let Slothy do this as well. General idea is we duplicate the loop body and place additional constraints that each of these instructions needs to be exactly n apart from the same instruction, the next iteration. So this way we maintain this periodic loop, and then we can run Slothy, and this then basically gives us a loop body that has the least number of stalls. Hiding some details here, but this is roughly the idea. In the paper, you can see what you actually need to do to make that work. And this is really, really powerful. This can find code that you look at and think, wow, I would have never thought of this by manually doing it. Or it would need a lot of time. One thing I also want to mention here before I get into the details is we have what we call a self-check. So this is a simple check that after the optimization, you check if everything is still okay. The idea here is you transform both your input code and your output code into a data flow graph, and then you check that these data flow graphs are isomorphic to each other. And this is actually very easy to do given the permutation, the reordering permutation, and Slothy outputs this. So this is very simple. It's not really formal verification, but we found this very useful, and it also helps you to debug your architectural model. Looking into some results, so we do have NTT results on the M profile, of course, implementing the Helium instruction set. And we do, compared to the CHES paper 2 years ago, do get comparable speed, but we have much more compact code because of the software pipelining. You get much more compact code. You don't have to unroll everything like what was done in the previous work. For A profile cores, or Neon cores, we looked into the A55 and A72. Again, looking at Kyber and the lithium entities. There was comparing to another CHES paper from 2 years ago. We get faster code than what was in that paper. And in some cases, it's a little bit more compact. And we also looked at in-order cores, where like the A55 is an in-order core, and there this becomes very useful to model, like to use Slothy to optimize code. We then also looked into elliptic curve crypto, so XFF19. We looked into this because there is a very nice implementation that's a hybrid scalar vector implementation. So it's doing some computation on the scalar unit and some computation on the vector unit. And this is very tedious to do by hand because you have to kind of alternate vector and scalar instructions, and they don't really, these are different computations, so it gets very hard to understand. And by using our tool, you can actually just write them separately and then let the tool do the interleaving. And we get faster code, and it's much cleaner compared to the previous code. So let me conclude here. So we have this tool that can help writing faster assembly with less work. You can try it today. We have a tutorial online that helps you to get started. If you have any questions, please talk to us. We have multiple microarchitectures already. We're adding more, but there's already quite some support for microarchitectures. We looked at a bunch of different crypto schemes. It seems to be useful for very different types of code. And we keep extending this. So we're still working on more projects, and we will add more crypto and more features. One thing I want to mention here is that actually this has found some use in practice now. So this work was not done by us, but by John Harrison's team at AWS. So they formally verified our XFF19 implementation using whole light, and now integrated into the S2N BigNum. So that's their BigNum library that they use for their crypto library. And there on Graviton 2, the scalar multiplication is actually 74% faster than what they previously had there. And that's quite a lot of cycles that they save. And since they have quite a few of these instances, they save quite a lot of money with that. And the full XFF19 keygen and scalar multiplication is actually more than 3 times faster than what's in OpenSSL. But this is not entirely due to Slothy. They also did some other things. For the formal verification, they tell me that this actually made easier using the approach of Slothy. So they proved the input correct and then proved that the optimized code is still correct. And they have used this for more elliptic curve cryptography now, where they again prove correctness using whole light. But there they prove the input correct, and then they use automated equivalence checking of the output. And there's also a recent blog post how they use it for RSA. So we have some ongoing work. So we're looking into Ketchak. We're looking into more CPUs. So we're looking at the Cortex M7, which is a dual issue CPU where we think this, well, we know it's going to be useful to use Slothy for that. And we're also looking into adding more features to Slothy. So for example, we're adding automatic register spilling, which cannot sometimes be useful. One thing that I want to mention here, because we're at CHES, we also think that Slothy could be useful in eliminating pipeline leakage. So if you can model your pipeline leakage, or avoiding pipeline leakage as constraints, then we can use this tool to actually automatically get rid of pipeline leakage. And we think this is a promising future direction. We haven't done anything on this yet, but we think this is useful. And there is a CHES paper this year called Prevention of Microarchitectural Leakages in Mass Embedded Software, where they phrase some things that to us read like we could express this in Slothy as constraints. So hopefully we can look into that in the future. So if you're interested in that, please come talk to us. With that, I would like to thank you very much for your attention.
So thank you for the nice presentation. We have time for some questions. For Matthias, you may have questions. Yes, please.
And please come up to the microphone. Yes, thank you.
Thank you, Matthias, for a great presentation. There's something you mentioned in the beginning, but you didn't elaborate it further in your slides. Could you clarify why this paper was so painful to you?
I think you need to ask that after a beer.
Okay. So we'll take it offline.
Yeah.
I have a question. So all the architectures are ARM based. So your starting language is also something like ARM assembly?
Yeah, it's executable assembly, yes.
Okay. And would this work then just for ARM, or what would be the difference if you would like to do that for x86, you would have to start from somewhere completely different, right? Or would like a compiling, sampling work?
So the question is, can you model your microarchitecture as constraints in a reasonable way? If you can do that, then this tool can be used. So you can add other architectures. So we have multiple architectures. So you could add more architectures. If x86 is the promising target, I don't know. We haven't tried. For certain RISC-V cores, there's certainly interest in doing that, and we think it's going to work for. Yeah. Does that answer your question? Or?
Yeah, thank you.
So what happens when you start with C code and let the compiler do its work and then take the assembly code of the C compiler as input? Can you still improve upon what GCC gives you, or can you not?
I mean, we haven't tried this because we wanted to have control over what instructions are being used. You could theoretically do that, yeah. There's no reason why you cannot do that.
But there's no experience in how this improves or not improves the performance.
Sorry, say again.
But you don't have experience if you can improve performance over output.
We don't have any data on this.
Okay, thanks.
I was wondering, how confident are you in the correctness of the tool? So you mentioned that Amazon people did formal verification to check the equivalence on the output. Do you see this as something strictly needed if you want to deploy that code, or do you see this as not needed precaution and they were a bit too paranoid in doing that?
So you mean in general proving code correct, or proving that Slothy doesn't break anything?
Proving that Slothy doesn't break stuff.
I mean, if it's easy to prove the equivalence and it seems not to be too hard, then it's useful to do that, yes. Then you don't have to trust Slothy you don't have to trust the model of Slothy at all. So I think this is a useful thing to do, yes. In theory, if the Slothy architectural model is correct, since it doesn't change any instructions, it shouldn't matter, but we don't want to trust these models. So yeah, I think it's useful.
Hello, representation. Question is regarding to AWS. You said that they went through the process of certifying this. Can you talk about what did they take as input? That they took the output of your tool and what the process was, whatever you know.
So for the X519 implementation, they basically added annotations to the input assembly that helps with the verification, and then Slothy would maintain these annotations, and then they could prove that they're equivalent. I do not know the details of that proof, so I can't really comment on much more than that.
Yeah, because the question is whether the tool itself, the Slothy tool, becomes part of their framework that they have to actually certify as part of their solution, or they just take the output and just go to the output and edit the output a little more and just say that's what it is. Okay.
The latter. You only take the output of Slothy and prove it's equivalent to the input. You don't need to worry about Slothy at all. Yeah.
So quick question from me. When you say optimizer, I hear side channel. So the question goes in the direction, like, is it part of your model of the microarchitecture, to not allow optimizations that would introduce microarchitectural side channels? The one side. Second question, could I run masked code through your tool? So two separate questions.
Okay, so I think since we only change scheduling, the only thing that you can introduce is like pipeline leakage. And this is something we have not looked into yet, but we think the tool can actually help to eliminate that. If you can model it as constraints, we want to model this pipeline leakage to avoid it. Of course, the way the Slothy currently works, if you run it on mass implementation, it could introduce more leakage. Yeah.
Hey there. Quick question from the chat. Do you consider to add Cortex M0 where register allocation spilling is the problem or is a problem?
What is the last sentence? Register allocation?
Cortex M0 where register allocation and spilling is a problem. Do you consider adding that? Is a problem.
Is a problem. We have not considered the M0. We're looking at M4 and M7. If anyone would like to do the M0, we would be more than happy to have that added. I don't see any reason why it would be hard to do that. You can, if you have spills in your input code, that's not a problem. You can model dependencies through memory. We're also looking into automatic spill code generation, but this is harder.
Okay, this paper has drawn a lot of attention. So if you have more questions, I'm sure that Matthias will be here available. Now let's thank the speaker again. Thank you very much. We are ready for the coffee break.
Yeah, coffee break outside.